we have here the same original data that we had in the preceding model. Okay, y versus x. The 5.8, 12.3, 23.7, 48.1 should be familiar to you. Now, in looking at this data, it's not immediately obvious that it should be an exponential model. Maybe it's a power function model of some kind. And maybe, for example, the power function ought to be, that linearizes this model, ought to be y to the 0.6 power. Turns out that that's not really the best power to use, but we could do a power function model using something like this. So, if we transform y by doing y to the 0.6, we end up with these data. Now, checking the differences here, they're not quite constant, they're really increasing. So again, y to the 0.6 might not be the best model. I think 0.4, 0.5 would be a better power to use. But we can follow the same procedure that we always have. Okay, we graph the linearized data, the y to the 0.6 versus x. We get some graph points that really are kind of curving upward. We do our best to fit a straight line that models this. Now really I fit that line a little bit too low. It should have been up much closer to this one. We could have gotten a lot closer to this one without getting all that much further away from these, so we could have reduced the average distance of the line from the points. But let's just accept this one for now. And at least this bad model seems to be about y to the 0.6 equals 2x plus 3. Again, we can get the 2x plus 3 by estimating the y-intercept and the slope, or by taking 2 points on the line and doing a slope equals slope form of the straight line, and solving that to get the slope-intercept form. If this is the model that we use for the function, the model for the linearized data, then we have y to the 0.6 equals 2x plus 3. We can easily solve that for y by taking the reciprocal 0.6 power of both sides. The reciprocal of 0.6 is pretty close to 1.7, so we're going to say y is about 2x plus 3 raised to the 1.7 power. Now we come back and we plug that model in and we compare that model with our original data. Plugging in x equals 1, we get, for x we get 6.4, plugging in x equals 2 we get 15.4, and so forth, plugging in x3 equals 3 and 4. And you see this isn't really all that bad a model. We're off by 0.6 here, now we're off by about 3 here, and we're off by about 4 here, and we're low by about 7 here, so it's not that great of a model, but it still follows fairly close to the data that we started with. Of course, we see that our exponential model was much better. The one we got when we transformed with the logarithmic function, we were always within 0.1 or 0.2 of our data. And we saw, of course, that we should have been getting exponential results. We should have done well with exponential because that's where the data came from a set of exponential data. Remember the 6, 12, 24, 48. Had we used a 0.4 or 0.5 power or some other power, we could have gotten much closer, but we would never have gotten as close as we can get with a good exponential model.